Okay, at t equals 1.5 seconds. What's happening? The particle's position is the particle is moving to the right at a rate of, right out of space, 4.787 centimeters per second. To the right. Now they told me to put to the right.
To the right?
Yeah.
At a rate.
At a rate of 4.787 centimeters per second. But we have also said the particle's position is increasing at a rate of 4.787 centimeters per second. But since you guys are like physics geniuses, you're thinking that's a little weird, right? Yes. It's kind of weird. So maybe you guys already made the connection that the sign of the velocity tells you the direction that the particle is moving? Yes? Alright, cool. So let's make sure that you made the connection here. And I want you to make the connection between the slope of a secant line What does the slope of the secant line correspond to here? So in terms of position, what does the slope of the secant line correspond to? So how do I find the slope of the secant line? F of B minus F of A over B minus A?
Yeah.
Right, we did that like 2 days ago? Or 3 days ago? What do you think that that corresponds to regarding the position of the particle? The average velocity, right? So this would be the same thing as me doing P of B minus P of A over B minus A, which we said was just the average velocity on the closed interval from A to B. The next question says, what does the instantaneous velocity correspond to? So if I had instantaneous velocity, that would be like having what? In relation to the position function. P prime of some number, and that would relate to what? F prime of some number, kind of looks like a P2, right? Which is the what? The slope of the tangent line, right? So if I draw tangent lines on the position graph, I'm getting the values of the what?
Instantaneous velocity.
Instantaneous velocity, right? If I draw tangent lines on the acceleration graph, on the velocity graph, then I'm getting what? Acceleration values, right? Okay? So that kind of means that acceleration is the which derivative? The second derivative of what function? The position function, right? Acceleration is the first derivative of the velocity function. Okay, so you got to be careful when you're working out problems on the AP test to understand what they're giving you so you know how many derivatives to find. Sometimes they start you off already with the velocity function, so you don't need to get two derivatives, right? You just need one derivative to find acceleration. Cool? Be very careful and read carefully. All right, ready to move on to acceleration? Maybe?
Yeah.
Acceleration, what is acceleration? Is it also a rate? So it's a rate of change of velocity. Would it be a rate of change of the rate of change of position?
Yeah.
Yes?
Yes.
Could we say that?
Yes.
The rate of change of the rate of change of position?
Yes.
Yeah?
Sounds weird,
Sounds weird?
but it's right.
Because we said velocity was rate of change of position, right? Alright, cool. So, what we want to do here is we want to let v of t
I'm watching.
be the same thing as p prime of t, right? Or the velocity function. So when I reference v of t, I'm talking about the velocity function, okay?
Yeah.
If I want average acceleration on the closed interval a to b, how would I find that? So you said p prime of b minus p prime of a over b minus a? Could I also say v of b minus v of a over b minus a?
Yeah.
Yes?
Yeah.
Ooh, very good. Okay? Depending on what you're given, right? If they give you the position function, then you need to get its derivative and evaluate its derivative to find the acceleration, right? If they're giving you the velocity function already, then you can just use that velocity function. Good? How about instantaneous? Acceleration.
Give me a second.
It would be the second derivative of who?
Position.
Of the position, so this would be like p double prime at c. It would also be what? The first derivative of velocity, right? Or we could give it its own specific name. A of c, right? Okay, so when they give you a of anything, you know that you're talking about the acceleration. You should also know that you're talking about the first derivative of velocity, or that you're talking about the second derivative of position. Pretty good? Alright, so let's see if we can find those two accelerations, the average and the instantaneous. You ready? So we're still using the same function that we were using earlier, it's still the same units, but now instead of average velocity and instantaneous, we're finding average acceleration. Cool? So how do I find average acceleration? What did it say?
P.
I need p prime, right?
Of B. So first you gotta find the derivative.
Do we know p prime of t already?
Yeah.
We found it? What was it?
E of t times sine of t.
E to the t sine of t
Plus.
plus e to the t cosine of t?
Yeah.
And we know that that is also equal to v of t, which is the velocity. Are we good? So if I want the average acceleration, what's the formula I need to set up? V of 3 minus V of 1 over 3 minus 1. So now I need to evaluate 3 and 1 not in the position function but in the velocity function, right? Can we do that? Do we already have the 3 and the 1 stored? Yes? So all we really need to do is type in this equation, right? So e to the t sine of t, just kidding, plus e to the t cosine of t, right? And we get these two values. So we'd end up with negative 17.050 minus 3.756 over 2. And that gives us how much?
403. Centimeter. I
Yeah.
didn't even say
Why
anything.
is it in the green?
Yeah. Put that.
No, like on the
Same thing.
You just typed it all right there.
Yeah. Or you can just like copy and paste. But you do this, right?
No, but
And then you just switch
isn't
it.
there some shit?
Hold
Yes, you can put variables, you know, already gonna do that.
And you what?
Hold on, you test, you know.
Did I ask you?
No, you didn't. I'm saying you what I'm like.
Are
Alright.
we good? If you're getting different numbers, it's because you're not in radians. Maybe your friends are being mean and changing your calculator
No,
to
why
degrees.
No, else.
Maybe I'll do that tomorrow on purpose.
What?
Alright, what do we get? Negative 10.403, and what will the units be?
Seconds.
Centimeters per second squared?
Yeah, I told her.
Why are they squared on this one?
Acceleration.
Because this is already units, centimeters per second, right? And then down here we have seconds, right?
Centimeters second per second.
So it's a rate of a rate, so it's centimeters per second, which makes it centimeters per second squared. Yes? Alright, whatever. Maybe they just want to hear me teach. What is the instantaneous acceleration? So now we need v prime. Okay. So we know v of t is e to the t sine of t, right? Plus e to the t cosine of t. So in order to find instantaneous acceleration, we need the first derivative of the velocity. So we want v prime of t. So let's do it. Can I do it by hand? What's the derivative of this guy?
E of t.
All of that, right?
Yeah.
Yes or no?
Yes, sir.
Plus, now we need the derivative of this guy, which is going to be e to the t cosine of t. And then the first times the derivative of the second, what's the derivative of cosine? Negative sine, so that's going to give us negative e to the t sine of t, right?
Mm.
So does something cancel out? The e to the t sine of t? So how many e to the t cosine of t's do we have?
2.
So we have 2 e to the t cosine of t, and that's equal to v prime of t, which we could also say is a of t, right? The acceleration force. And can we now evaluate it at 1.5?
You're so young.
What's a at 1.5? Type it in your calculator. 2 times e to the 1.5 times cosine of 1.5. Could we have done all that on the calculator?
0.634.
Even with the position function,
Yeah.
right? We could have asked for the second derivative of the position function at 1.5. And it will give us the same answer that we're gonna get.
0.634.
0.634,
Centimeters.
and what would be my units?
Centimeters per second squared.
Centimeters per second squared.
Yeah, roughly.
Beautiful. We didn't write what they represent, right? So let's go back and do that.
I know, but also.
What does this one represent in
Centimeters per
words?
second per second.
On average, from t equals 1 to t equals 3, what can you say? Okay, so the particle's velocity is decreasing at a rate of 10.403 centimeters per second squared. Can we use acceleration to describe the position? No?
Yeah, concavity.
The concavity?
If you relate to concavity.
I don't even know.
You can? No? I don't think so. Alright, how about the bottom one?
Oh, no.
Yeah, you can't use acceleration to describe the particle's position, because if acceleration is negative, it doesn't mean that the position is, the particle is moving in a certain direction, it just means that it could be moving in the same direction, but not at the same rate.
Yeah.
You get me?
Yeah.
In other words, the particle could be moving to the right, but it's not moving to the right as fast, right? Right. You understand? Okay, so at t equals 1.5, what's happening? Particle's velocity is increasing at a rate of